Kish. Today I will be the moderator. Dear reporter, please start your presentation.
Good morning, ladies and gentlemen. My name is Balázs and I'm here to present problem 1 on behalf of Hungarian Team Red. First, I would like to start with the interpretation of the problem. The task can be broken down into 3 criteria that our solution must meet. First, we have to synthesize a mixture of compounds with the same uniform inorganic crystal type and the different chemical composition. And then we have to separate the record-holding particles from the mixture, and the criteria on which we select must be dependent on the chemical composition of the crystals. So, as a base for my solution, I choose hydroxyapatite, and there are many reasons for that. First, it's an inexpensive material. It has a well-defined crystal structure. It has many substitution sites into a variety of ions can be substituted, and also it has medical industrial relevance due to its biocompatibility. And here you can see the crystals like a schematic structure of hydroxyapatite. So first we have to prepare our crystals, and hydroxyapatite, abbreviated as AH from now on, is available from commercial sources in a powdering form. The first we have to do with this is to select uniform sized crystals, and it can be done easily using 2 filtration steps. Then we want to incorporate our crystals into an organic polymer gel that is uncorked onto a glass plate. And this is the so-called chromatographic plate because it's analogous to the stationary phase in liquid chromatography. So here you can see that we choose agarose for our organic gel. And now that we have our particles are in place, we can do the substitution. And if the plate was the stationary phase in liquid chromatography, the mobile phase is the aqueous solution of ions, of different ions that will flow through the system in a given direction. And some ions are retained in the gel due to the interaction between the ions and the crystal particles, and that would create a gradually decreasing concentration throughout the plate. And we do this treatment like 1 ion at once, at least 2 ions at once, like we have to have a cation and an ion, but between the treatment steps, the gel ought to be washed using distilled water. And now I've talked a lot about the ions that can be substituted onto the crystal particles. But what are these ions? And according to literature called cationic and anion substitutions in hydroxyapatite, the identified vicarious ions in bone and tooth apatites are fluoride, chloride, sodium, potassium, divalent iron, divalent zinc, strontium, magnesium, citrate, and carbonate. And what we have to do is we have to pair them up in a manner that the compounds remain soluble in water, and also choose a direction into which we want to flow the solution through the plate in a manner that no ions are flown, like the same ions aren't flown directly opposite to one another in subsequent steps, because that would obviously ruin our concentration gradient. And then we have to degrade our agarose matrix using heat and excess water. It's a quite simple step. And after that, we can separate our particles from it using centrifuge. And now comes the criteria on which we wish to select. Hydroxyapatite is the main constituent of teeth. And therefore, acid resistance of hydroxyapatite is a highly advantageous trait because it can prevent cavity formation because and acid resistance does depend on the chemical composition of hydroxyapatite. So we can use this criteria. And now comes the selection step. The crystal particles are first dumped into a solution bath consisting of sodium alginate and ascorbic acid, and it's an aqueous solution. Hydroxyapatite dissolves below pH 4.5, and therefore we use the ascorbic acid in the bath to set the solution's pH to 3, just to make sure that the crystal particles are dissolving, or at least start to dissolve. And as they dissolve, free-flowing calcium ions are released from the crystal. And sodium alginate, which is in the bath, reacts with these calcium ions, and it creates a gel-like precipitation that will coat our particles. And as the reaction goes on and more calcium leaves the crystal, the more precipitation will form, and this layer of precipitation, which is gel-like, will thicken, and so after a while the crystal particles will be entrapped into these alginate beads, whose diameter is dependent on the acid resistance of the crystals. Because higher the acid resistance of the crystal is, the less calcium ions leave the crystal, and therefore the smaller the alginate the diameter will be. And after that, we can just separate the smallest particle via a simple filtration step. In conclusion, I would like to state that I have solved the problem, so I proposed a way of creating a mixture of particles, which has a uniform inorganic crystal type, which is provided by the original hydroxyapatite structure, and then we separated the report holding particles based on acid resistance, which is dependent on chemical composition, so it can be used as a selective criteria. Thank you for your attention.
Thank you very much. Now the opponent has 1 minute to prepare.
Thank you. So first, I would like to ask whether the hydroxyapatite is stable in the washing step. I think the water might actually dissolve too much of the hydroxyapatite to make the solution viable.
Well, as I said, the
Sorry, it's a
hydroxyapatite.
monologue. It's his monologue. You can answer later. Thank you.
So anyway, I think the hydroxyapatite would dissolve as much as possible. Furthermore, I think your solution is overly convoluted. Use of metal oxides would be much better. They are cheaply available.
It's your solution, and you should speak about the reporter's solution, not yours. You can speak in English, please. It's our official language of the tournament.
I also think that anchoring to the chair is unstable with respect to washing as well. And you haven't mentioned the financial aspects of your solution, because washing usually requires plenty of water, which is a limited resource in our world due to overpopulation. So I think that you should save on that one. Furthermore, I doubt the alginate is going to be able to insulate the acids as you suggested in your solution. So I think your hydroxyapatite crystals will not be that different in terms of size, because they would eventually all dissolve under the action of an acid. Furthermore, the original question asked for properties of crystals with respect to which the specimens are selected with respect to. And you only mentioned one property, namely the acid resistance. So I would like to inquire whether you are prepared to have further properties with respect to which you can select or not. That's it.
Okay, thank you. Now the reporter has 4 minutes to answer.
So, about your first question, whether hydroxyapatite will dissolve in the wash step, and well, my simple answer for that is it won't, because it only dissolves with a pH 4.5, and the pH of distilled water at room temperature is at 7, so it won't cause a problem. Also, you asked about something about the anchorage, and I should find something about it. So it is anchored into the gel because the pore size of the gel is around around the size of the hydroxyapatite crystal, and therefore it cannot be washed away from the gel. Your question. Moving on to the question about whether alginate will insulate our particles from the acid degradation, and well, it would cause a problem if it would insulate it. It should not insulate our particles, because yes, you are right. After a while, it would degrade all the particles, but we want to stop the reaction at a point where we still have the crystals, because otherwise it would not be good for us. I think I have answered all of your questions.
Okay, then let's start the discussion.
Thank you for your exhaustive answers. However, I think that you didn't answer my question regarding further properties of the crystals with respect to which you can select.
Now I remember. You asked about. Yes. Yes, so you can separate for the most dense or the lightest particles from it via a simple density gradient centrifugation using this clarity solution that should work for density. And if you think about it, the property of acid resistance and density are like there are two properties, and then you can call it properties. So yes, I think I have sufficiently answered your question.
Yes, that's indeed true. However, you didn't sufficiently answer my question regarding the washing step. So how much water you use in that step? Step.
It's up to you as much as necessary to eliminate all the free-flowing ions in the system. Yes, I think that would answer it.
I don't think so, because water is scarce and people are thirsty in Africa. So I think saving water is crucial in every experiment we design. So unless you provide the exact amount of water which you use, I don't think the exercise is solved in an ethical manner.
Yes, certainly there are ethical concerns regarding this solution.
So how much water do you use?
Obviously, as you mentioned, we should limit the water usage because it's needed elsewhere in the world, and we have to think about the environment and the people. However, well, I can't give you an exact estimate, I'm afraid.
Exactly. Okay, so on a DLC plate, you usually see spots as you run the thin layer chromatography. However, you mentioned that here you would have distribution of concentrations, a concentration gradient, so to say. So how do you plan to achieve that?
You mean that we will have like spots with higher concentration around, like if you look at the plate, so that we will have like spots with higher concentration? Well, that's not the case. We won't have that. But we will have gradients in a given direction.
But why?
Well, as I mentioned before, the ions can interact with the hydroxyapatite crystals. It can be absorbed on the surface and then dissolved, and this interaction will slow down the ions, and that's how.
Thank you.
Okay, thank you both. And now it's time for the reviewer.
Dear ladies and gentlemen, my name is Dorina De Bretani, and I'm here to review the presentation and the debate about the problem number 10. First of all, I would like to thank both the reporter and the opponent for their work. We could see a fascinating debate about the topic of the synthesis of a specified uniform inorganic crystal. As to begin, I would like to start with the reporter. About the presentational part, his slides were neatly organized, so colorful, and maintained the logical structure, and also contained the slide numbers, and it was easy for the opponent to refer to the text he mentioned. And the slum sides of the reporter were a bit messy. His speech and the presentational style was clear, calm, understandable, and very, very confident. To move on to the scientific part, he explained how he would prepare the crystal, and he worked with hydroxyapatite. His solution contained great ideas and demonstrated personal engagement. He clearly explained the method of the separation step and the selection process, conditions, and the role of the alginate. I really appreciate the cute birds on the slides. It made the report more eye-catching. All in all, I think the reporter fulfilled all the criteria of the problem, and so he deserves a high mark. And I would like to turn to the opponent. His speech and presentational style was polite, composed, and convincing. The questions he asked were reasonable, relevant. However, he mentioned the question not strictly related to the solution of the reporter. He asked if the hydroxyapatite is dissolved in the washing step, another related to the degradation of the particles, and one about the density. He asked how much water could be used in the washing step. He claimed that we should save water because of these conditions. And he asked how the TLC method works in this specified case. The discussion part was very fruitful. The reporter included many extra slides to the questions.
Sorry, your time is up. Thank you very much. And now it's time for the jury's questions. Attila?
May I? Okay. So my question would be to the reporter. So you are substituting the +2 positive charged calcium with +1 positive charge potassium and sodium. how do they fit into the crystal structure? Is there any space for two ions?
As it's been described in literature, I think I can say that yes, they can fit, like you can fit two ions in that place, because they said that it's possible, so it should be.
Very well.
If it's possible, I would like to ask you if you could provide us with an exact correlation between the thickness of the alginate coating and the acid resistance of the mixture or your compound.
Well, I don't have an exact correlation number. Like I can't say that if the alginate is at one case is twice as thick as in the other, it will be twice as more acid resistant. But what I can say is that that if the coating is thinner, then the crystal will be more acid resistant than the other crystals with thicker coating.
That's it.
So, how would you determine the exact chemical composition of your best particle? What methods would you use?
I don't think I need to determine its chemical structure. Like if it's not in the text of the task, but I can think of some things. So perhaps you could use a method such as, I don't know, elemental analysis for it. It should work. I mean, it wouldn't give like an exact place where the substitution have happened, but at least it can give information about the chemical composition of the crystal.
If I may. So you mentioned that you paired up ions that don't precipitate with each other. However, would the calciums that are leaving the crystal not precipitate with the carbonate ions, and wouldn't it cause a problem?
Well, that's a very valid concern, and I just try to get back to my ions. So, yes, for sure. The calcium ions leaving the crystal will form a precipitate with fluoride, for example, and carbonate too. It's not a question. It's not a matter of debate. It will happen. Like, however, it won't be a problem because it can be washed away during the washing step, since the particles that are formed in this way is way smaller than the pore size of the agarose gel.
So, beforehand you addressed the problem of hydroxyapatite crystals leaving your gel based on the pore size of your gel matrix. What I would be interested of if you have a estimate for the flow rate of your solution, and how would it affect the hydroxyapatite crystals leaving the gel matrix?
Well, as the opponent asked before, we should limit the use of water, that's for sure. It's not a matter of debate. I can't really answer like how much should you limit the flow of water through the system, because I mean, yes, the amount of water is dependent on the flow that we use. But again, I think it cannot be said with 100. Like I cannot say you an exact data without doing some experiments first.
Answer the last question.
My question is to the reviewer, because you ran out of time, there was no time for the conclusion, so I would like to ask you to tell us your conclusion about this debate, please.
Thank you very much. I just missed the single sentence. In conclusion, I just wanted to say that the reporter fulfilled all the criteria of the problem, and the opponent highlighted very well the missing points of this wonderful presentation. Thank you.
Okay, thank you. And it's general discussion now. Does anyone has a question? Danish?
Okay, so you mentioned that you initially began with hydroxyapatite particles, which are in the range of 100 to 500 nanometers in size. And so I would just like to ask you if that disparity in the sizes of the initial particles would be like a limiting factor, because then you again measure particle size at the end in terms of the alginate coating. So would that you have initially different particle sizes would influence the outcome of your measurements?
If it were the case, then it would be a problem, but it isn't the case, as I said. Like the first thing that we do with our hydroxyapatite powder is to filtrate it so that we will have uniform sized crystals. And as I may go to my appendix, the ideal size of the crystal is around 190 nanometers. And so we should try to filter for this. However, obviously you can't filter for this exact number, but you can, find particles with a range of 185 to 195. So I don't think that it would pose a problem.
Okay.
Thank you. I would like to ask a further question to the reporter. Do you think that the shape of the hydroxyapatite beads and consequent changes or variations in the relative surface area thereof might affect the dissolution rate and consequently render your solution inappropriate?
Well, yes, if I may, I'm sorry. So, yes, you should use porous hydroxyapatite because that would increase the surface into which the substitution can take place. So yes, you should use porous hydroxyapatite.
Any other questions? Okay, then if no more question, then it's time for the jury to write down the marks. Are you ready? Okay, then grades for the scientific part of the report: 5, 5 minus, 5 plus. Grades for the presentational part of the report: 5 minus, 4 plus, 5 minus. Grades for the opponent: please show the marks. Okay, 4 minus, 4 and 4 minus. And grades for the reviewer. 4 plus, 4 and 4. Thank you very much. We have a 5 plus, so we need explanation.
Okay, so I gave 5 plus for the scientific part because I believe that the reporter presented a really unique method and solution for this problem, and I believe that this could actually work, and in fact it would be a very useful experiment to carry out in real life in the lab. All of the scientific facts were supported by evidence and by literature, and I did not find any major or in fact minor scientific problem in his solution, and therefore I believe that he deserved the best mark for the scientific part. And I would like to take the chance to talk a bit about the other marks. I gave 5 minus for the presentation part because even though the slides were really nice, readable and eye-catching, the reporter started answering to the opponent's monologue during the opponent's monologue, which something that the reporter should not do. I gave the opponent 4 minus because there was an irrelevant question about the amount of water which he kept asking again and again. He started talking in another language which is not English at the beginning of his monologue, and that's something that the opponent should absolutely not do because the language of the International Chemistry Tournament is English, and therefore everyone should talk in English all the time. And also the opponent started presenting his own idea or his own solution, which is also something that the opponent should not do. The opponent should reflect to the presented solution. Otherwise, the opponent had relevant and scientifically good questions. Therefore, his opposition was not absolutely bad, but there were serious mistakes that he made. And I gave the reviewer 4 because even though she summarized some aspects of the debate, she ran out of time, and therefore she had no time to say a conclusion, and there's a whole mark going for the conclusion in the review, and therefore 4 plus would be the best that I can give according to the rules. However, I think that in the review there were too many factual details and she listed too many questions the opponent asked, and that's not exactly what a reviewer should do. In my opinion, a reviewer should include some examples in her review or in his review, however not all of them, and should reflect to the debate and to each of the rows more generally. I think that's my explanation. Thank you very much.
Thank you. Does anyone else has something to say?
If I may, I would add a little bit of explanation to my mark for the reviewer too. What I lacked is that she did not point out these formal mistakes Bence just mentioned in the review, and in my opinion she should have reflected on the fact that, for example, the opponent used a foreign language. That's all, thank you.
So thank you everyone for this great round. This is the end of the round.